Picture this, it's 1948, and the Union Pacific Railroad is staring down a crisis that could cripple their entire operation. Freight traffic has exploded by 50% in just 1 year. Their legendary steam locomotives are bleeding money faster than they can count it. And their shiny new diesels, they're failing spectacularly on the very route where the railroad needs them most. The railroad's board of directors issued a challenge that seemed almost impossible. Build us a single locomotive powerful enough to replace 5 diesel engines, make it strong enough to haul thousands of tons of freight over the Rocky Mountains, and do it at a price we can actually afford to run. What emerged from this desperate demand would become the most powerful locomotive ever built in America. A machine so loud it was banned from entering certain cities, so hot its exhaust could melt asphalt, and so revolutionary that it rewrote the rules of what rail transportation could achieve. This is the story of Union Pacific's gas turbine electric locomotives, the giants that conquered Sherman Hill and then vanished almost overnight. Let's dive into one of the most fascinating chapters in American railroad history, the mountain that wouldn't yield. To understand why Union Pacific needed such an extreme solution, you need to understand Sherman Hill. This wasn't just another stretch of track, it was a railroad engineer's nightmare carved into Wyoming granite. Stretching between Cheyenne and Laramie, Sherman Hill represented the highest point on the entire transcontinental railroad at over 8,000 feet above sea level. The westbound grade climbed at 1.55%, a figure that might not sound intimidating until you trying to drag 5,000 tons of steel and cargo up its relentless slope. This hill had been tormenting the Union Pacific since the 1860s, when the Transcontinental Railroad was first built. The original surveyors discovered this route in 1867, and while it was the best option available, it was never easy. Early trains faced grades as steep as 1.92%. And winters brought snowdrifts so deep that 13 snow sheds had to be constructed to keep trains moving. By 1948, Sherman Hill had become more than just a physical obstacle. It was a bottleneck choking the railroad's profitability. The post-war economic boom sent freight volumes surging. Every day, rail yards filled with boxcars, tankers, and hopper cars, all waiting their turn to climb the grade. Dispatchers worked around the clock, shuffling schedules and praying for clear tracks, but the backlog never eased. The railroad's massive big boy steam locomotives could muscle their way over Sherman Hill, but at a devastating cost. Each big boy consumed mountains of coal, required constant maintenance, and needed crews working in exhausting shifts. A single big boy cost over $500,000 annually just in coal, water, and labor. The maintenance yards overflowed with worn-out parts and exhausted workers. Union Pacific had hoped diesel power would solve their problems. Diesels were supposed to be the future, cleaner, and more efficient than steam, but reality delivered a harsh lesson. A typical diesel locomotive of that era, like an EMDF-3 or an Elco FA, produced only around 1,500 horsepower. That's less than a quarter of what a big boy could generate. To move heavy westbound trains over Sherman Hill, the railroad had to lash together for 5, sometimes even 6 diesel units. This created its own nightmare. 6 engines meant 6 fuel tanks to fill, 6 sets of wheels to inspect, 6 chances for mechanical failure. If one unit stalled or lost power halfway up the grade, the entire train could be stranded, blocking the main line and cascading delays throughout the system. The railroad was trapped. Steam was bankrupting them. Diesel fleets were proving just as expensive and operationally complex. Union Pacific needed a breakthrough, something radical enough to change the equation entirely. The jet age comes to the rails, while Union Pacific struggled with Sherman Hill. An engineer at General Electric named Vincent Mertz was looking at the problem from a completely different angle. Mertz had been working with gas turbine technology for aviation applications, and he saw something that others missed. If a turbine could power a fighter jet through the sky at supersonic speeds, why couldn't it haul freight trains over mountains? The timing couldn't have been better. In the late 1940s, jet engines were proving themselves in military aircraft. The technology had matured rapidly during World War II and the subsequent Korean conflict. Fighters like the F-86 Sabre and MiG-15 were rewriting the rules of aerial combat, powered by gas turbines that delivered unprecedented thrust. The fundamental principle of a gas turbine is elegantly simple. Air rushes into a compressor where it's squeezed to high pressure. This compressed air mixes with fuel in combustion chambers and ignites in a controlled explosion. The resulting hot gases blast through turbine blades, spinning them at incredible speeds, up to 6,900 revolutions per minute in locomotive applications. The exhaust screams out at temperatures exceeding 800 degrees Fahrenheit. What made turbines so attractive wasn't just their power, it was their mechanical simplicity. A diesel locomotive engine is a complex symphony of thousands of moving parts, pistons slamming back and forth, crankshafts twisting under tremendous stress, valves opening and closing in precise timing. Every component is a potential failure point requiring maintenance. A gas turbine, by contrast, is fundamentally just a spinning shaft. There are no reciprocating parts, no complex valve trains, no cylinder heads to crack or gaskets to blow, just continuous, smooth rotation. In theory, this meant dramatically reduced maintenance compared to diesel engines. The numbers Mertz was looking at were staggering. A gas turbine could deliver around 10 times the horsepower per pound compared to a diesel engine. A single turbine could generate 4,500 horsepower in early designs, later reaching an incredible 8,500 horsepower. That was 5 times what a standard diesel could produce, and it matched or exceeded even the mighty big boy steam locomotives. The railroad industry was deeply skeptical. Critics pointed out every reason turbines should fail on rails. The engines spun so fast that any flaw could lead to catastrophic blade failure, sending shrapnel through the engine housing. The exhaust was hot enough to scorch tunnel linings and bridge timbers, and the noise, engineers joked it was like standing behind a jet at takeoff, except you couldn't walk away. But Mertz and his team at General Electric pressed forward. They built test facilities in Schenectady, New York, where turbines ran at full power for thousands of hours. Engineers measured vibrations, tested new alloys capable of withstanding extreme temperatures and rotational forces, and designed intake screens to protect against birds and debris. They also solved a critical problem: how to convert the turbine's high-speed rotation into usable tractive effort. The solution was to use the turbine to drive a massive electrical generator. This generator produced electricity that fed traction motors mounted on the locomotive's trucks, turning the wheels. It was the same basic principle as a diesel electric locomotive, just with far more power. Union Pacific's leadership watched these developments with growing interest. The old solutions were failing. Steam was economically unsustainable. Diesel lash-ups weren't living up to their promise. The turbine offered something genuinely new, a chance to leapfrog the competition and solve Sherman Hill once and for all. In 1948, General Electric completed a prototype, designated GE 101, and numbered up 50 by the railroad. Painted in Union Pacific's distinctive armor yellow, this machine looked like nothing else on American rails. It had a cab at each end, resembling Alco FA diesel units, but the sides were covered with air intake louvers. Inside beat the heart of the jet age, a gas turbine producing 4,800 horsepower, with 4,500 available for traction. The prototype proved the concept worked. Union Pacific never actually purchased up 50. It remained General Electric's property. But the extensive testing demonstrated that jet turbine technology could be successfully adapted for railroad use. The stage was set for production models that would push the boundaries even further. Birth of the big blow. If the prototype impressed Union Pacific, the production models would astonish the entire railroad industry. Between 1952 and 1961, General Electric delivered a fleet of 55 gas turbine electric locomotives to Union Pacific. These machines evolved through 3 distinct generations, each more powerful and refined than the last. The first generation consisted of 10 locomotives, numbered 51 through 60, delivered in 1952 and 1953. These units built directly on the lessons learned from the prototype, producing 4,500 horsepower each. They featured a distinctive body style, with a single control cab and numerous air intake louvers along the sides. The railroad was so impressed with these first 10 units that in 1954 they ordered 15 more, numbered 61 through 75. These second-generation locomotives had similar specifications, but sported a different body design. The sides were narrower, allowing running boards along both sides of the locomotive. Crews nicknamed them veranda units after these walkways. These also featured much larger fuel tenders, holding 24,000 gallons, compared to the original 7,200-gallon capacity. But the true giants came with the third generation. Between 1958 and 1961, Union Pacific took delivery of 30 locomotives numbered 1 through 30. These weren't just bigger, they were in a completely different league. Each third-generation unit consisted of 3 separate sections stretching nearly 200 feet from end to end. The A unit contained the control cab and an auxiliary diesel engine for moving the locomotive around rail yards. The B unit housed the main turbine, a General Electric Frame 5 gas turbine with a 16-stage compressor, 10 combustion chambers, and a 2-stage turbine section. The C unit was the fuel tender, essentially a rolling oil tank on wheels. Together, These units weighed over 800 tons, fully fueled, and could produce an astounding 8,500 horsepower. No locomotive built before or since has matched this raw power output in American service. When the railroad claimed these were the most powerful locomotives in the world, they weren't exaggerating. The turbine itself was a marvel of engineering. It spun at 6,900 revolutions per minute, a speed that required cutting-edge metallurgy and precision manufacturing. The slightest imbalance could cause catastrophic failure, so every component was manufactured to aerospace tolerances. Starting one of these behemoths was a carefully choreographed procedure. Crew would first start the auxiliary diesel engine in the A unit. This small diesel drove a generator that could supply electricity to various systems. To start the main turbine, the generator essentially acted as a motor, spinning the turbine up to speed before fuel was introduced. Initially, the turbine burned regular diesel fuel during startup. Once it reached about 80% of maximum speed, the fuel system switched to the heavy fuel oil stored in the tender. This transition had to be carefully managed, as the heavy oil needed to be heated to proper viscosity before it could be properly atomized and burned. The fuel that made it possible. Here's where the story gets really interesting. The economics of these turbines depended entirely on one crucial factor: fuel cost. And Union Pacific had found a way to run them on what amounted to industrial waste. Instead of burning expensive diesel fuel, these locomotives ran on heavy fuel oil, specifically a grade known as number 5 or bunker B. This was the thick, tar-like residue left at the bottom of refinery distillation towers after lighter products like gasoline, diesel, and kerosene had been extracted. In the 1950s, refineries had limited uses for this heavy residue and sold it for pennies. At just 3 to 4 cents per gallon, this heavy fuel cost a fraction of what diesel did. This price differential was the secret sauce that made the gas turbines economically viable, despite their prodigious fuel consumption. But burning this cheap fuel came with serious challenges. At room temperature, heavy fuel is almost solid, far too viscous to pump or atomize. The solution was to heat it. The fuel tender was lined with electric heating coils that kept the heavy oil at around 250 degrees Fahrenheit. At this temperature, the sludge became liquid enough to flow through fuel lines and be properly atomized in the turbine's combustion chambers. The system worked, but it wasn't without problems. Heavy fuel contains impurities and trace elements that diesel fuel doesn't have. These contaminants caused erosion of compressor blades and deposits on turbine components. Union Pacific continually refined their fuel specifications, eventually settling on a specially processed version of number 5 fuel that reduced but didn't eliminate these maintenance issues. The fuel capacity of these machines was staggering. The third-generation tenders held up to 24,000 gallons, even burning fuel at rates that would horrify modern efficiency experts. This gave the locomotives incredible range. They could run for hundreds of miles between refueling stops, spending more time hauling freight and less time sitting at fuel racks. This fuel strategy was brilliant, but it was also the Achilles heel that would eventually doom these magnificent machines. Conquering the mountain. When a gas turbine locomotive left the yard under full power for the first time, everyone within miles knew it. The sound was unforgettable. A high-pitched scream like a dozen jetliners, spooling up simultaneously. Windows rattled, dogs howled, the ground seemed to vibrate. For the crews assigned to operate them, the experience was simultaneously thrilling and terrifying. Engineers reported that the cab shook continuously. The heat radiating from the turbine section could blister paint 50 feet away. The noise was so intense that crews wore earplugs for their entire shift. But when the throttle opened and the train began to move, all discomfort was forgotten. Sherman Hill, where steam giants had labored and diesel consists struggled, the gas turbines took the grade like it was nothing. A single turbine locomotive could haul 100 loaded freight cars up that punishing 1.55% westbound grade at 40 miles per hour without breaking a sweat. The performance statistics were extraordinary. Each turbine averaged over 100,000 miles annually, though they made up less than 2% of Union Pacific's locomotive fleet. These machines hauled more than 10% of all the railroad's freight. Read that again. 1 out of every 10 tons of cargo crossing the Rocky Mountains rode behind a gas turbine. The power was so overwhelming that it sometimes exceeded the capacity of the equipment it was meant to move. There's a documented incident from 1960 where a turbine started up Sherman Hill a bit too aggressively. The coupler on the first freight car literally snapped in half, sending the rest of the train rolling backward down the grade. The turbines could generate so much tractive effort that they could break steel couplers rated for hundreds of thousands of pounds of force. Operating procedures had to be completely rewritten. Engineers learned to be gentle with the throttle, especially when starting a heavy train. The turbines delivered their power in a smooth, continuous surge, unlike the rhythmic beat of a steam locomotive or the gradual buildup of a diesel. It took a delicate touch to harness all that force without damaging equipment or breaking couplings. Crews developed a love-hate relationship with these machines. Yes, they were noisy, hot, and uncomfortable to operate. But they were also incredibly powerful and, when running well, remarkably reliable. A turbine could move more freight faster than any other locomotive on the roster. For engineers who took pride in their work, that capability was addictive. For 2 decades, the gas turbines didn't just meet the challenge of Sherman Hill, they dominated it. Critics who had called them expensive experiments had to admit these monsters could move mountains of freight. The fatal flaw, despite their impressive performance, the gas turbines had a vulnerability that engineers could never completely solve. Fuel efficiency, or rather, the lack of it. A diesel locomotive can idle quietly, sipping fuel while waiting at a signal or in a siding. A gas turbine, on the other hand, guzzled heavy oil at nearly the same rate whether sitting still or hauling 100 cars up a mountain. The turbine had to maintain a minimum rotational speed to stay operational, and that meant continuous fuel burn. This inefficiency wasn't a problem when heavy fuel cost just pennies per gallon, but the economic landscape was shifting in ways Union Pacific couldn't control. Through the 1950s, refineries viewed heavy residual oil as a byproduct with limited applications. But in the 1960s, the petrochemical industry exploded. Chemists discovered that heavy oil could be cracked through various processes to produce feedstocks for plastics, synthetic materials, and other products. Suddenly, the stuff nobody wanted became the foundation of a multi-billion-dollar industry. The price of heavy fuel didn't just creep upward, it soared. By the late 1960s, it cost almost as much as diesel fuel. The economic advantage that had justified the turbine's high fuel consumption evaporated virtually overnight. Internal railroad documents from 1967 and 1968 spelled out the harsh reality. Turbine fuel costs had doubled in less than a decade. When economists ran the numbers, combining fuel and maintenance costs, each turbine now cost nearly twice as much per mile to operate as a modern diesel locomotive consist. The break-even point had disappeared entirely. Making matters worse, noise complaints were mounting. The turbine's jet engine roar, once seen as a badge of power, had become a public relations nightmare. As suburbs expanded along rail corridors in Wyoming communities, residents packed town council meetings with complaints about sleepless nights and vibrating windows. Though no formal bans were enacted, political pressure mounted for Union Pacific to keep these noisy monsters away from populated areas. The railroad tried parking turbines in remote sidings when not actively hauling trains, but this only worsened their already poor fuel efficiency. An idling turbine burned fuel while generating no revenue. Meanwhile, diesel locomotive technology had advanced dramatically. New models from General Electric and Electromotive Division produced 3,000 to 3,600 horsepower per unit, with dramatically better fuel efficiency. 2 or 3 modern diesels could match a turbine's power while burning far less fuel and producing less noise. The end of an era. By 1970, the verdict was inescapable. The first turbines were retired in August 1968, and the fleet was systematically withdrawn from service over the next 2 years. The last operational run of a Union Pacific gas turbine locomotive occurred on December 26, 1969, when turbine number 7 hauled an eastbound manifest freight from Cheyenne to North Platte. Most of the locomotives were scrapped by the late 1970s. The tenders were recycled for various purposes. Some converted to water cars for maintenance of way operations. Others eventually used to support Union Pacific's Heritage Steam Locomotive program. The running gear, trucks, traction motors from many turbines were recycled into new diesel locomotives, giving them a second life in more conventional form. Only 2 third-generation turbines survived. Number 18 was preserved at the Illinois Railway Museum in Union, Illinois. Number 26 found a home at the Utah State Railroad Museum in Ogden, Utah. The gas turbines were outmaneuvered by forces beyond Union Pacific's control, rising fuel costs, public pressure about noise, and the relentless march of diesel technology. For all their raw power, they couldn't overcome basic economics. Legacy and lessons. Looking back, it's easy to see the gas turbine experiment as a failure. After all, these locomotives operated for barely 2 decades before being scrapped, but that perspective misses the bigger picture. For 20 years, Union Pacific ran the most powerful locomotives ever built in America. They conquered Sherman Hill, hauled incredible amounts of freight, and demonstrated that radically different approaches to railroad motive power could succeed. The turbines proved that thinking beyond conventional solutions could yield remarkable results, even if those results weren't permanent. The engineers who designed and operated these machines pushed the boundaries of what was possible. They took technology from the jet age and successfully adapted it for railroad use. They solved countless technical problems that skeptics said couldn't be solved. And for a time, they gave Union Pacific a competitive advantage that no other railroad could match. Today's railroads chase efficiency and quiet operation above all else. Modern diesel locomotives produce more power per gallon than the turbines could dream of, and they do it without shaking windows or drawing noise complaints. That's genuine progress, and it's hard to argue against. But sometimes progress requires taking bold risks on unproven technology. Sometimes it demands machines that don't fit polite expectations. Sometimes it means building something so powerful it seems almost excessive just to prove it can be done. The gas turbines were never meant to be the final solution. They were a bridge between the steam era and the modern diesel age. They bought Union Pacific time to figure out better solutions while keeping freight moving over Sherman Hill. They proved that a railroad could think creatively and take calculated risks on revolutionary technology. As we face new challenges in transportation and energy, maybe there's a lesson here. The need for raw, disruptive power hasn't disappeared. As global shipping demands surge and energy sources evolve, we might need to dare to build machines that challenge limits even when they don't fit conventional wisdom. Progress isn't always quiet. Sometimes it shakes the ground. The gas turbine locomotives of Union Pacific represent one of the most audacious experiments in railroad history. They were too loud, too hungry for fuel, and ultimately too expensive to operate long-term. But they were also magnificently powerful, mechanically innovative, and for 2 decades, they were exactly what the railroad needed. Could a new turbine ever roar again? Probably not in the same form. But the spirit that created them, the willingness to take aviation technology and adapt it for the rails, that pioneering attitude remains valuable. Who knows what technologies we'll repurpose for tomorrow's challenges? The big blows are gone now, silent monuments in museums. But their story reminds us that sometimes the boldest solutions are the ones that make the most noise. What do you think? Would you have wanted to ride in one of these thundering behemoths? Let me know in the comments below.